Okay, let's resume with the afternoon session. We have Antoine Levitt talking about integration results, like a different time. Very good. So you have an hour. I'll give you a 10-minute warning.
Okay, so thank you. Yes, so when Michael asked me abstract. So we talk about 2 words. One we did a couple of years back with a and one which is more recent with one which so yeah, and the first, with the whole scheme of the thing is the numerical integration. So as we've seen the topic of this workshop, some hidden errors, and one of the biggest errors in solid state DFT is K-point separation. Right? So it's not the biggest. It's one of the probably the top three being first the XC error, second the pseudo-potential error, third this guy. So it's nice in the sense that it's systematically improvable. You can just tune your parameter to make it converge, but it's very often superscript. Okay? So I'm going to talk about it. So first I will explain a bit of what my plot to expose in solid states, what are green zones and what circles as well. Then I will show some elements of analysis of these type of things, and I will end up talking about analytic continuations, computations of resonances, and all this kind of stuff. Feel free to interrupt. Okay, so Green zone and supercell. So assume you want to model solids, right? So if you want to model solid, you're just going to take a finite system and make it 10 to infinity. The way you should do that is by supercell approach. Not actually that humanity, but intensively, right? So you take your unit cell of the crystal, you make copies of them, of your cell, that gives you a supercell. It's very convenient to have fairly boundary conditions on the edges of the supercell, right? Because that doesn't break velocity and you can exploit that. And then you take that and you let it tend to. So because you've not broken the velocity because of your periodic boundary conditions of the edge of your cell, of your supercell, you can use velocity to use the Bloch theorem. And the Bloch theorem tells you that the eigenstates of your Hamiltonian, the eigenstates of your Hamiltonian can be looked for in the form of Bloch waves. Right? And Bloch waves look like this. They are periodic with the periodicity of the green cell, modulated by an oscillating factor. And this K here makes this whole function be supercell vector. Because the velocity of the supercell. So K belongs to this discrete Riemann zone. So AI star are the vectors of the reciprocal lattice. If you just have a cubic lattice, this is just unit vectors. And here looks like this, right? So it's discrete vectors that make this whole function there. And then here are your eigenstates, the eigenstates of the I'm completely ignoring the fact that you may have on-chart Hamiltonian, self-consistent, and so on, and just taking the Hamiltonian for granted. There will be other talks later, and that's not on how to quantify this. Okay, then what is the total energy of my supercell? Well, the number of electrons, the occupied states are going to be those which are lower in energy than the Fermi level. So you occupy all the states such that epsilon K is lower than the Fermi level. And this fixes the Fermi level because you want the number of electrons in your supercell to be the actual number of electrons you have in your supercell. That defines epsilon F of the level. And the energy is just the sum of the eigenvalues. I'm assuming independent electrons. Okay. Then we take L to infinity to make this bigger. And what you find is that these sums turn into integrals, and these are the relations I'm going to say. It's that energy is given by an integral of the Brillouin zone. That's the same with a strike integral. It's just the integral normalized by the volume of the domain over which you are calculating. You just sum the energy of the occupied states. Okay, that's your bulk energy. That's L. And again, the first level is determined by this condition that fixes this. The question I'm going to be asking is, what is the speed of convergence of this to this? Okay, which is what you do in practice. In practice, you have your supercell approach, but you don't do it with the supercells. You just do it by computing the function on the unit cell, which is much faster, of course, but you have this sampling of the unit one that you may find in fact. Okay, and again, it's very important because of errors in practice. So the concept of band structure comes from this analysis of the epsilon and decay, which is energies. And when you have metals, you have band structure that looks like this, no gap. When you have an insulator or oscillator, you get a gap. Okay, if you look at the spectrum, you get this. So far, so good. Okay, now here comes the mass. If you have a gap system, you have an insulator or oscillator, you have a set of occupied bands and a set of unoccupied bands. And so the energy just looks like this. And you know it's been, okay, as mathematicians do. We don't like factors of two. So I just have this thing. This is the definition of the energy. And now, what is the error you make when you replace this integral with a sum? Okay? Because when you sample the brain zone, this is exactly what you replace the integral with a sum. What you can show, this was well known in the literature, but even in this paper, is that the convergence is exponential with some universal rates. This is good. Okay. This is slightly surprising for mathematicians because you're doing this, which is like the worst way to compute integrals. You just replace integral by a sum space. So usually that doesn't work. Right? If you apply the standard estimates of numerical like this, you get 1 over L convergence, and this is very slow. But in fact, this is much better because of error cancellation, right? If you replace this integral by this function, you will underestimate here, overestimate there, underestimate here, and in fact, you will get much more accurate results than what you would expect. And mathematically, you can see that by the fact that this quadrature is exact for the harmonics that are not too fast. Okay. So then, the question of analyzing the convergence of this integral just becomes the question: what is the decay of the Fourier coefficient of this function as a function of k? It's smooth and very function of k. I get the first harmonics right, and so the error I made is proportional to the magnitude of the Fourier coefficients I don't get. So now the question becomes, what is the decay of the Fourier coefficients of this guy? So here you have the eigenvalues. The dependence of eigenvalues on the parameter is not really clear in general. If the eigenvalues cross, they might not be smooth, and so the Fourier coefficient will not decay very fast. But in fact, here you have the sum of gap eigenvalues. You can prove by Antoine Levitt by convex arguments that this guy is actually super smooth. It's actually analytic in the strip, and therefore its Fourier coefficient decay exponential. And this is what you prove the convergence rate. This was in insulators. Insulators are easy to converge with respect to k-parts of them. The fun part is metals. So what about metals? Well, metals have Fermi surfaces. right? So instead of this guy simplifying to just sum, you have this factor here that tells you that you should integrate only the states that are below the family. The problem is that the topology and the geometry of the Fermi surfaces can look very, very complicated. So this is a very common site where you can visualize the Fermi surfaces of different materials. If you're here, then it's good. If you're here, not so much. And accordingly, this kind of problems is much easier, it is much simpler to integrate than this kind of problems. Okay, so the assumption we make in order to prove a scale, the assumptions we make are first, your metal has to have a Fermi surface, so this set, this crossing set has to be non-empty. You don't want crossings on your Fermi surface, so if you say things like graphene, your Fermi surfaces that are degenerate, it's the nice surfaces that are of reduced dimensions, this you don't want. And you also don't want flat bands, because also you get degeneracies of the Fermi band. So you want something very nice and parabolic, on which you make an intersection that gives you a nice surface. Yeah.
Just for clarification, you want to measure zero set of flatness, but not like.
They can be flat wherever they want, but not at the Fermi level. So, yeah. And in practice, not close to the Fermi level. Okay, so under these conditions, you can define the density of state as a smooth function. Right? So the density of state is you take the Venn diagram, you sort of collapse it on the line here, and that gives you a function. Here there's a band, so the density of state is non-zero. Here there's nobody, the density of state is zero. And you can define this, then this integration function. But take away, if the assumptions are verified, then the density of state is, you see it here, right? This is the Fermi level. At the Fermi level, there's no fancy business going on, and the density of state is, if you've got flat bands, you've got singularity of the density of state. So that to prove us here. Right? Okay, so then what do you do? Well, you have many methods. This, either you do the very naive method, replace this integral by just a sum, or you can try to interpolate the band structure. And so our results show that if you interpolate the band structure to some accuracy, some or higher order method, for instance, then the error you make on the Fermi level are of that order. This is very hard code because you compute intersection of surfaces that are defined by polynomial equations. It's not very nice. This is the math code. Okay, so this is the error of the level, and for the energy, something fun goes on, which is that this Q, which is the order of the integration you use for the interpolation you use to define the integration domain. This is of higher order. And this is a fundamental argument, which is that, okay, if you screw up on this guy, you screw up the shape of the Fermi surface, right? So you should normally screw up on the same order the energy, but you actually don't, because the energy near the Fermi level is constant, the Fermi energy, and the error you make on this is basically proportional to the order to the Fermi level times the error you make in the determination of the number of electrons. But since the number of electrons is determined self-consistently, that error is zero. And so to be in order with zero, and this is why you get higher proportion. This is a fundamental argument, I'm going to skip the proof. This is very, very specific to the energy. So in the literature, you find statements like the energy variation in the Fermi surface, which is right, okay, so this is the part where you don't use any temperature, so you use zero information just by setting up states. Another thing you can do is, instead of doing this the naive way or the interpolated way, you can use temperature. And temperature, instead of having a function that is 1 when your state is occupied and 0 when it's not, you have family direct functions. You can get fancy and do all the type of spring or just you can do Gaussian spring, Maxwell Baxton, which is this funny little thing that goes up and down. But basically, what you do is you replace your quantities by this T here that means to change, you put in the function. Okay. So it's a regularization parameter. Typically, it's a temperature, but mostly the reason why it's used in this application is not because of physical effects, it's just to make the mass easier. And now the nice thing about this is that this integrand is a smooth function of k. So you don't have singularities on the space, you have a very nice integrand all in the brain term. And so you can apply this, the convergence meters, and you see that you can compute this as you would an iterator, just by regular cohort. So we have two sources of errors between this guy in here, which is what you actually compute, and which corresponds. You have the fact that you cheated, you've replaced your 0 k to by finite, and then you've integrated your finite temperature. Okay. So we can try to compute and to see what these errors look like. So here, this is a definition. You have different types of smearing that are more effective than others. And okay, if you do family direct or Gaussian smearing, functions that look like this, then basically what you find is the error you make is of order t squared on the temperature. Okay. If you get fancy and do this weird oscillating functions, you can get higher. This is what they are designed. So how do you prove the same things? Write down, this is for the number of electrons, for instance. If you have this guy, just count the number of electrons that are in your system. You can write this as an integral of the distribution function times the density of states. And then you can do a change of variable to this guy. And now you see that as t goes to 0, this should be bad. Yeah, okay. As this guy goes to 0, this goes to basically a delta function, and you times t, that you remember t. And so basically, you find that this will converge to the right thing. So, like I said, as t goes to 0, this converges to the heaviside function from 0, and so you get the right thing. But the way you get the right thing, the higher order terms, you can compute them explicitly, and you can estimate them to the result. Now, so this for this term. Now you can look at the second term. The second term is you fix the temperature and you want to converge that temperature by curvature. And so you apply the previous theory, but now for a function that is smooth. But it's smooth, but it still is pretty sharp, right? So the function will be sharp, smooth, but sharp at the free surface. And you can compute and quantify how much it's sharp. Basically, what it turns out to be is that if you want to quantify the way a function is sharp, you look at that function in the complex domain. And typically, if you have a function that looks like this, it's relatively sharp, it will have a pole near the axis. It's an anti-quantification. And therefore, the Fourier coefficient will converge to some mean, and therefore you will get some inequality. Okay. Now there's a difference here between the family-back function, which is analytic that has poles. We've seen that before in the talk of the start, and the Gaussian function, which is entire. It doesn't have any pole anywhere in the complex plane. And therefore, you will get different results. This is the math for the one interested. Basically, you have to do something fancy, control same to prove the amount you need to accuracy. The result is that you get exponential convergence with some prefactor that depends on the temperature. The lower the temperature, the slower the convergence with respect to that. And you even get super exponential convergence with Gaussian time scaling, again, because the Gaussian time scaling is entire. So this is a fancy bit of complex analysis. It's pretty fun to do. So the end result is that the pair you make between your actual energy and the energy at finite temperature with temperature is a sort of two terms. The first is the fact that you replace your temperature by your zero by finite temperature, and the second is the fact that you have temperature. And it looks like that. It's not exactly like that. It looks like. So as t goes to 0, this guy goes to 0, but this guy is harder to converge. And based on this, you can do things like optimize this with respect to t for a given L. For a given L, what is the optimal temperature? This tells you that up to log factors, you should take the temperature going as 1 over R. Okay, first conclusion of this part. We've proven things essentially as expected. Insulators are easy, metals are hard. Metals are easier when you have non-deterministic assumptions of the shape of the Fermi surface. If you have a real Fermi surface, it's even worse. This is borne out by how this goes. This only concerns the very basic schemes. Now there are many improved schemes to get better convergence. So you can use this Shirley method, there's many functions you can use to get better. It's going to get this great. Okay?
What about Methusel maximum?
So Methusel maximum is covered by these things. Methusel maximum is because of speeds and is based on the fact that you have this focus. So it's a better approximation of the
Can you go back to the very last slide before the conclusions? So if I take temperature to 0 in that equation, it tells me that there is a constant error.
Yes.
But my prediction is like, they don't do smearing.
At finite now.
Yeah.
Yeah.
Oh.
So if you fix it, so
If I increase the L at the temperature,
yes.
I can still get 0 error.
No, you get temperature. If your target is 0 K,
I don't use any smearing.
if you don't use any smearing, then based on this, you'll be right. The instruments are not sharp if you don't use this. And in which case,
I should converge to the correct answer.
yes,
Yeah.
this is the previous results with this result of question. You should indeed use converge. Depending on the scheme, you converge, depending on the scheme.
This is for metals.
Yes.
I know you didn't want to go into this, but I still was interested in maybe some pointers towards, when you don't have a uniform cable mesh, for example.
Yeah, for sure. So now we have to do this, mostly for 2D systems. Because Hans is trying to do it. He says it's good to be checked. And most of more information. So in theory, it should be better to do adaptivity. The problem is adaptivity only makes sense if you have a relatively fine cable mesh, which might be challenging. But if you are targeting like very, very high accuracy applications, for instance, benchmarks, you might be able to follow it. Yeah.
Last information from Gus is that it doesn't work.
Really? So I got information from 3 months ago, and 3 months ago it's
1 week ago.
so you need me.
So she was very surprised. I was very surprised. And I asked him if he's in touch with you.
No, sorry. Adaptivity doesn't work. Higher order works. I think this is.
Yeah, the adaptivity.
Yes. Okay. Yes.
So these will be consistent.
Sorry. Yes. Adaptivity doesn't work, at least for the size.
Yes.
Higher order does work. But if you read, so I'm sure it's tested things with reasonable accuracy. If you go to unreasonable accuracy, like we've seen yesterday, then it might, meaning real benchmark systems, then it might be good.
Are we doing general? Do you have more slides?
Yeah.
Okay.
No, but it's
These are my
okay.
questions.
No, it's okay. I have more side, we don't.
I wanted to ask about stress because everything that you've shown is for energy convergence, and for us, stress is what's really stressing us because sorry, but it's because when you change the way, right? When you compute it, it's equivalent to making a change in the and it's coupled with the cut, right? Because when you change the unit cell, the whole Brillouin zone shrinks, but it's finitely sampled. And the whole thing, like the errors that we see there are much bigger than the errors we see in the energy for a fixed cell.
They should be covered, stresses should be covered by our results, which means just that.
But you don't get some funny changing exponents?
No, it's just the prefactor is going to be much bigger. So we got results on density, we don't, so forces, for instance, will be covered. Stresses, I'm not sure, but I think should be.
Because it's like the forces are so that's very easy to believe.
Yeah.
It's the same in the energy, but the stress is coupled to the shrink. You change the K point, and then because of the finite.
You can pass them again to the.
So you move your sampling points now.
Okay, I don't want to say yes, it's a bit, but
something to think about.
Yeah. All right. So, okay, second part, analytic continuation. So, analytic continuation turns out whenever you want to compute the state of things more accurately. Assume you want to compute density of states. So, again, this density of states looks like this. And you can write it as this, which the definitions don't like because it's delta function, so you're regularizing with this funny thing, which is just saying that instead of a delta function, you put a coefficient or a Lorentz vector. So 1 over 1 plus x squared and 1 over 1 plus x squared is the imaginary part of this function, but the interest of this relation is that you link the density of the state to the Green's function. The density of state is some kind of transparency of the boundary value of the result. Okay. Now, this is okay. You can do it exactly the same as before. You can do interpolation of the time structure and computation of this. You can define the temperature and replace this delta function by finite function. You lose analyticity when you do that. And there are cases where you really want to get the analytic structure of this D of E correct. And when I say analytic structure, I mean in the complex you want complex analytic extensions of that D of E. So one case where this comes up is for resonances computations. I'm not going to detail too much about the resonance computation. I'm just going to give an idea of something we developed for resonances that could be of interest for people today. Okay, so this is a simpler problem, a simpler quadrature. Assume we want to compute this guy. Okay. You are given a phi of epsilon, which defines some kind of energy distribution. And you want to compute this integral of phi of epsilon over z minus epsilon, when z is in the complex plane, the upper complex plane. This is completely undefined, but now what happens if I take z to go down to the real axis? As we've seen for density of this computation. What happens is that this integral becomes singular. Right? So as the integral becomes similar, your quadratic scheme is going to be. But here there's a very simple solution, which you can deform this integral in the complex plane. Right? Instead of integrating like this, you can integrate like this. And if you deform it this particular way, there's no problem with the z going into the mid-axis. So that defines a way of computing this guy on the axis or even below the axis. Yeah, so this is for the very easy case of this instance. Now we don't have this, right? We have things that depend on k, and we have integrals that look more like this. Okay, with some integrand that depends on k over z minus epsilon of k, and you integrate over k, not over epsilon. Okay, so here the contour integral is a bit harder to see, but you can still do the contour integral. I'm doing one case. You can still do the contour deformation. It's just that the way you have to deform the contour in K is not always low. You have to deform the contour in K in a way that pushes the identity sign of K below the axis. Right? So sometimes you have to go up, sometimes you have to go down, and the way you have to go, whether you want to go up or down, is given by the sign of epsilon prime of K. Derivative of dependent G, which is the group velocity. So in some sense, it's not completely surprising that this epsilon prime of K shows up. It shows up before to define the surface. It's also the group velocity. So if you have a zero group velocity, your waves don't go out of the simulation box, that's good. But this works as long as you do it in this particular way. And now, if you have a higher dimensional problem, not just you cannot do the easy contour deformation that's below, but you can do this variation here, which is a multi-dimensional contour deformation. So instead of deforming a contour, you deform a whole plane or a whole box. Right? So it's hard to visualize. You deform the Bayesian zone into the complex plane. The proof is one line of the formula, it's just a multi-dimensional generalization of contour integration. And now, where you have to take the k, instead of doing integration of k, you have to take the k into the complex hyperbola zone, and the way you have to do it is to be proportional to the velocity. And if you do it this particular way, you will be guaranteed, at least for small deformations, you will be guaranteed to push the spectrum in the angle down. Okay? And now you can apply this to the full problem with the full gradient function. You can apply this also to just make k, you deform k to k plus I ki, where ki is of this form. You choose other functions in order to not work where you don't do what you play, but otherwise go into the direction of the velocity. Okay. That works as long as there's no similarities, which are anyway non-analytic points, so there's no good there. These schemes, you can do it completely local. It's only units of computation. It's quite fast because it converges exponentially with respect to the variables. Right? You deform your integral, but once you deform your integral, you are integrating an analytic function, which is super efficient. For people who might know, there's a method called complex scaling that works whenever you want to compute resonances of molecules and so on, which basically deforms the coordinate from X to a complex coordinate. So this is a kind of generalization of complex scaling to periodic systems. That might be small. Here's an example for a simple 1D diatomic chain. So you take this Hamiltonian, you have got nearest neighbors complex is equal to step 1, and you have the diatomic chain, so we have A, B, A, B. The spectrum, you've got two bands, and if you do this complex deformation, you can do things like this. This is a plot. This is a plot in the complex plane. And this defines the region of analyticity of the wind function. So the wind function is analytic over this whole thing. If you want to compute here, you can. So So we define an analytic extension of the green function, and therefore of the density of state. So for instance, you can apply this to graphene. Graphene is a very simple model of time binding model of graphene. Here, chemical interactions, the very standard model of graphene that has an analytic DOS compute. It's not nice, but you can just look it up in the paper. So that's the reference in black. You can apply the smearing methods we've seen before, or you can do this fancy deformation trick. So this fancy deformation trick is you push the eigenvalues below the red axis, and then you compute the DOS just by taking the values out. Okay? And the result is that it's not great near the bandages, but it's pretty good when you're in the flat form. When you're here, it's super good. Okay? We tune the parameters here, so this is actually more smart. We tune the parameters first. Okay? So that's one thing you can do with this method. You can compute density of states in a very accurate way. Another thing you can do is find resonances. So resonances, I'm not going to go into details, but reason because it might not be interesting. So basically, resonances are poles of the analytic contribution of the green function. So they generalize bound states, they are finite lifetimes, they are interesting for a number of applications. So they are poles of the analytic contribution. And if you want to propagate this on H is H0, H0 is a periodic recurrent constant graphene, and you perturbate locally, you put it effect. Okay. You can define the green function, you can continue the green function, and if you find poles of that analytic contribution, that's a resonance. You can do that by the resolving formula of the Bayesian equation, which tells you that you can express the green function of H as a function of the green function of H0. Right? So for instance, here is in action on this problem. So you take a sheet of graphene and you put an atom somewhere. And here, the depending of this is the same that tells you whenever there's resonance, and you see that there's a resonance here just below the green axis. So that the imaginary part of this guy would be the lifetime of the state. This you can compute with the continuation method. It looks like this, which is very good plot. So this is the resonance state. Okay, so you put an atom here. The width of the circle is the magnitude of the state. The color is the phase. So you have a state like this, and the state actually expands outwards. It's a resonance, so it sends energy outwards, and you can see this, which is very fast. So that's it for the resonance part. So right now we apply this to simple heat models. It can be in principle extended to 3D or complicated TFT. We don't know yet. It could be interesting to compute other kind of quantities, conductivities that might be hard to compute by other ways. Thank you very much.
We have quite a bit of time for questions.
Yeah.
So let's see. I'm just check if there's anything online or questions. I don't see anything online.
Yes. So first you specified this cutoff function.
Yes.
Needed for like
Just two portions.
okay. So I think we can say
So the purpose of this function is that you know what to do to push the poles. To push the poles down, you know what to do since this expansion involves this is the wrong way. It only works near the region which will be down, and otherwise you don't really know what to do.
I want to go back So the first part of the talk, the building zone sampling. Your result for the analysis, the same discussion of activity. There are adaptive schemes for selecting steering parameter given a building zone sampling. This somehow, I'm not sure if that was the context of the activity that was brought up, but we find it quite useful to do this kind of schemes compared to fixed steering.
Yes.
Especially when doing like a form of transport. Can you prove that they're essentially rigorously better than doing non-adaptive? And like, what is practically the best strategy one should use, I guess?
Okay, so from bounds we have what's going on. In practice, it's very hard to say because it depends on the factors and those we have absolutely no control over. So mathematically, what we prove is that there's two sources of errors. So okay, so how do you see that this thing is function of the what do you mean?
I mean, that's some schemes, I think, from Eagle Souza and
Because I know where
you look at the velocities and
yeah.
There's a problem. I mean, the velocities, the 2 points in the building zone.
Yeah.
I mean, there's probably many ways of doing that.
Yeah.
I'm just curious, like, is there a provable optimum?
Yeah. So there's a provable optimum of the bound. Our results say because that's the bounds. The bounds say there's two errors, t squared, let's say, and exponential minus L. So if you want to optimize this for t at a given L, the optimum is around 1 over L. It means exactly what is 1 over L around this some dependent function. So indeed, it's way better to adapt the t as you increase the sampling. It should be something like 1 over L.
I think that actually the formula has exactly that.
Yeah.
And there's some free factor.
The free factor, yes, indeed, is probably related to the family velocity. Yeah. Okay, so technically, if you really take 1 over L, I'm not sure you get convergence of this guy, of the sampling error. Just because as you define the mesh, the function gets harder to integrate. It's easier to integrate, but as we define the temperature, the function gets harder to integrate, and this effect, if you take t is equal to 1 over L, maybe don't compensate. But since, since this is exponential, as long as you go a bit faster than 1 over L,
That's interesting. You rigorously show that that's actually not a bad strategy at all.
oh no, it's definitely just taking this. But it's not completely, yeah, two factors is more.
Yes. Is there a take-home message in terms of the choice of the type of steering, or is that a bit more nuanced?
So mathematically, yes, just take the higher stores of you can, but that's always the take-home from math, right? Because the math that you asymptotically goes to this, three factors. Three factors and three asymptotics, and there's not much I can say about that. This is in practice. I think in practice people find that people is good. We don't want to do it for it. So that makes sense. Also, this cool experience is more.
I have another small question. So when you showed, like now the second level, when you showed the convergence of the graphene Lorentz function, especially the oscillations near the edge, I mean, I understand getting the edge is hard, but I don't know, intuitively I would say here this building is sort of better, right? It's nicer to have the edge smeared over than oscillation.
It depends what, so what we were interested in is this like below the limits, and that you cannot get with so that was interesting. This is what it's about this. To compute the losses, I guess it depends on the accuracy. Our method is exponentially convergent, so if you really want high accuracy, it's going to be better. For low accuracy, again, as you say, it's really not bad, right? But it doesn't seem complicated. the deviation of zoom is not. Here it does make quite a bit the one, whereas the red one is more. So near the singularities, it's the nice thing of the smearing is it will be sensible around singularities. Like it will be just blur. And blurring is better than just doing crazy sensitive.
Yeah, but then you want to get both.
Depends what you want and which region you want. But we need a lot of connectivities when you have to switch.
The last one, last qualification. And in the very beginning, you mentioned that there's exponential, surprising proof that there's exponential convergence for anything with a spectral gap. Is this mathematically somehow related to the exponential localization of one-year function?
Yes. So the simplest relationship is nearsightedness, which is the orthogonality matrix. Smoothness in K space is the same as decay in K space. The K space is fully transformed, so there's something smooth. So if you want to have something that decays quickly in your space, it has to be analytic in some region of the space. Analytic is like the better form of space. So that's the you get exponential convergence. So we prove this exponential convergence in K space, or it's just a quadrature, essentially. The other way to see it is that it's a super method. So if your thing is very localized, you have a big super it's the real space that counts. Just see what you do last in this
Hey. Thank you. Good. Okay, now we have James Kermode from Warwick, telling us about uncertainty quantification and multiscale modeling.
Thanks for asking. It's great to be here. Emails, so I'm struggling to get here. What I do on my phone, if I miss something, then please let me know. By way of motivation, the kinds of systems that we're interested in modeling in my group are those that combine chemistry and mechanics, chemical mechanical problems. Things like fracture, friction. So typically need quantum mechanical accuracy to describe fractional bonds or regulation of quantification, but we can't afford to model our system. So in the past, I've used things like Kermode to provide a localized description of bond breaking the fracture, embed that in classical software. That helps a lot with dealing with large systems, doesn't help you to address all time steps so much. So more recently, I've been joining in efforts to build machine learning style potentials and participants and also augment Kermode learning style. So a good way to automatically generate the potentially use. But all of these problems also simultaneously create a requirement for good understanding of uncertainties, so we can apply complicated quantities of interest that depend quite sensitively on the details of the method. So to pick a sort of motivating example of something like that too, this is a MD simulation of dislocation glide in nickel-based supernovae. So we have two different phases: gamma phase, which is pretty much the nickel, and then a harder precipitate phase at the time, which is 3 million. We're interested in trying to understand why dislocations get in interfaces between these two phases. So with around 3 in that phase, it gets stuck. You want to do something like that, well, there's potential. It's challenging. You need to consider both random and fact knowledge uncertainties, esoteric uncertainties, respectively. In the potential, in the way that you construct the simulation cell, the way you parameterize it, and potentially also algorithmic uncertainties in the way that you carry out DFT calculations, like reference training data or do the integration itself. Of course, I'm not going to tackle all of those, I'm focusing on one or two. But I think it's really good to try and have the big picture in mind. The other reason that I got interested in uncertainty over the last few years is because it's one of the things that we've built into the training center, helping to how it works. So we've got a sense of the doctoral training main texas, modeling heterogeneous systems, bringing together quantum mechanical and continuum systems across the scales. And we train students both in how to work across disciplinary barriers, projects of students to different disciplines, how to make sure that the software that they write is right away in PhD to support research software engineering. And then relevant for this workshop, we also teach how to incorporate uncertainty models. And that's the module that I teach in censoring. It's helped me a lot to understand a bit more about these techniques. You have to figure out how to teach something, that's when you really have to get to grips with. There's another sensor that I'm involved in, work sensor modeling. The aim of that is to try and take those things which is traditionally developed in mathematical sciences, physics, computer science, to try and improve linkages to the application make graphs. Our focus is to get engineering with often you can't immediately apply the algorithms changes what extensions to apply them to realistic systems. Okay, let's zoom in a little bit on what we're going to cover today. So I want to first mention a couple of examples, one quite old and one recent, on a structure level, so trying to quantify initially the uncertainties that arise in relations because of our inexact knowledge of the exchange correlation functional. And then later we'll move on to also model parameter error and multiform error. As I say, this is reasonably old work. It's not something that I've continued since we did this a few years ago, but I wanted to include it because it seems quite well aligned with something that's workshop. Resonates with a lot of results that we'll get later. I'm happy to go into more detail in the discussion for a little bit here. So essentially what we do is we model the exchange correlation energy because it's PFT. Actually, we only modify the exchange part, take the correlation directly from PV to keep it simple. We also freeze the densities at PV densities, but then we compute correction here. And this is kind of in the spirit of the ETH functional that many of you will be familiar with the Bayesian or some more of exchange functionals. It's just that we've tried to be a bit more explicit about how we do the Bayesian mechanics, which allows us to propagate densities a bit more easily. So the way that we define the exchange energy is through an exchange energy density depends on the electron density, gradient density, and exchange density, and that can be expressed through an exchange constant factor that boosts the exchange over that of the electron gas. And essentially, we write out a linear model for that, which has a bunch of coefficients, and the basis is standard in the drum polynomials, and then we fit it. And the difference from standard fit is that we try to get a probability distribution multiplied by estimate from these coefficients. The way that we do that is the very standard Bayesian approach. So we assume that the data, which in this case is experimental observations of atomization energies, follows the proposed linear model on average, but with some contaminated distance from Gaussian limits. So we have Gaussian distribution for our experimental observation energy for each one, our coefficients times our basis functions, some precision. And we can write down priors, people know that they're going to work out, so it's typical conjugate priors because that makes the integral in order to get the posterior analytic. So we take a normal distribution for the lengths, some initial mean, and covariance. These are defined through hyperparameters that optimize innovators, and then we have some noise parameters for distribution. And essentially, we use standard techniques. We use automatic elements detection combination with a element detector machine, so that we can have quite a big basis set. So what I'm showing here is a 10 by 10 grid of these coefficients, of these John polynomials, and the ones that are shown with small points are the ones that have been sent to zero to avoid any fitting by the relevance detector machine. So we only end up with a few coefficients, so we have quite a good description overall. This is what the ensemble of exchange functionals. I've shown two slices through that, one with constant gradient density, and a second with constant gradient of the electron density. And you can see we get not just a line plus 1 and 2 standard deviations. We've got access to full posterity that's analytic. In this case, we can draw samples from that and then use multiscale to propagate through to other quantity structures. Energies, simple solids, points show the experimental data to get a distribution of predictions. See, we didn't include any magnetic materials in our training database. No physics comes out for free. You still need to put in the right threes. You can look at things like constants or Bolt moduli in a similar way. We actually also, if you're interested in what I would maybe a little bit further, we propagated errors through to band gaps as well. You can do that either just in Shine GFT or with a basic particle approach. As I said, it's quite a long time ago, and I'll continue to work actively on this. I'll be happy to talk about what we did. One or two slides briefly on something that Christoph mentioned yesterday on parameterizing Hamiltonians directly from TFT data. So this is work with large collaboration involving Christoph and Reinhard Mauer's groups, and also Genevieve, who's with us, amongst others. I think Leeway is probably online as well, which I think was driving force behind these sorts of work in the end. So what we do is we take observations of Hamiltonian overlap matrices distributed in a local atomic basis, and we find a way to represent them that take covariance of the required symmetries. And further, you also see an on-site plot with Hamiltonian, so the interactions between two orbitals sitting on the same atom, or an off-site plot. That's here, where we're interested in interactions between distinct atoms. So overall, lots of Hamiltonian have macrovariant structure that's given through the bigger D matrices. If you rotate the structure, this is what happens. So Hamiltonian, and we first of all represent the blocks using a relatively simple basis set, function basis set. For the on-site blocks, that's really just the same as what you would do if you were trying to learn an electric potential, whereas the off-site blocks, the environment of interest is the environment of the bond. So we center it on a bond, we have a cylindrical envelope rather than a spherical envelope on the bond, and we have this construction for the basis set. We integrate over the group, the relevant symmetry group, and what we end up with are linear models for blocks in several to get Hamiltonian. So we have this E basis here, which get by integrating these initial bases over the relevant symmetry group and there's some definitions. So this saves you the SCF, but it doesn't save you the entire type box. We assemble it for Hamiltonian. It's essentially a sort of generalization of the type binding, in that it's not limited to two sets of approximations, but have a full representation of all the extractions.
Can I ask you one thing?
Yeah.
So you are predicting the non-orthogonal Hamiltonian, right? Have you tried, because I mean, when we did this, we found that actually predicting the non-orthogonal Hamiltonian gives you very good accuracy on the matrix elements of the non-orthogonal Hamiltonian. But then, if your basis set is not a minimal basis set that is very well conditioned, the errors of the spectrum becomes catastrophic. And it's actually much better if you care about the spectrum to predict a loading orthogonalized Hamiltonian.
Which isn't a problem. I guess the downside, the downside of which is the loading almost at far away.
Yes, exactly. But I'm wondering if you pick a minimal basis set, or is this a large?
It's close to minimal. It's not completely minimal. It's small.
This is something that we should discuss, because I think that one of the things that is really bugging me about this is that it gets really hard it gets much harder when you go to serious basis sets.
It always rejects first, right? So you could start with a large basis set and do a linear.
Yeah. But then if you do a linearization, you get actually long range. No, linearization, it's basically like a little bit like loading. So I think it's an interesting problem.
Yeah.
And it's, in a sense, it's error propagation, right?
Yeah.
Because it's
So the reason for including this here is exactly from an error propagation point of view. So what we get out are also the overlap matrices that can analyze them, compare the band structures, and the densities of states that get
Can you speak up a bit? People on the Slack say that it's very hard.
People on Zoom. I'll do my best. So we use band structures and densities of states and compare them to the reference ones. The error bars that we get here are not predictive error bars. These are a posteriori error bars. So this is just propagating from the known error and ultimately through to the error spectrum. The next step would be scale all the way and also errors in the internal metric sense entries and propagate them through. Okay, so I'm happy to talk more about that afterwards, but I just wanted to include it here because it's relatively recent and topical. Times we've got we've been in some other area. But really, I wanted to focus on interest potentials. That's what I'll talk about for the remaining 12 minutes. And this sort of follows on from Ian's poster. If you haven't had a look at that already, then still get a chance to do that. This might go online. Just follows on. What Ian is doing is using an ACE model and doing it similar ways as I talked about. The first way is basically regression and using samples from that series distribution of potentials to propagate increased coefficients. That's one way to do things, and what I'm going to talk about now is an alternative approach based on Gaussian process regression. This is what's used in the UGAP framework that we'll be familiar with. Just to briefly introduce what happens when we train Gaussian process. We start off with primary functions that ensures smoothness with the correlation between the value of the function at 2 points separated by some distance given by some variance thermal. For illustration purposes, show a simple square exponential thermal. We can condition that Gaussian process on those observations, which leads to an updated Gaussian process. Posterior is a Gaussian process which is has an analytic analysis. Or showed these formulas yesterday as well. And yeah, the attractive feature is the posterior variance and covariance estimates. What I want to dig into a little bit is how we can make that very useful. So maybe just before getting into that, there's another use that we can put Gaussian processes to, and that's to act as surrogates for particular quantities of interest. So let's say we want to look at parametric uncertainty in a calculation of the interest. Take an example of the vacancy formation energy in a simple model for silicon. So we can start off by doing some sensitivity analysis, find the top few parameters, and then we can use this GPU machinery to fit a probabilistic surrogate model for the mapping from interatomic parameters through to quantities of interest. That works out well you don't need very many points to be able to accurately do this mapping, and then you can use it, for example, to run very large ensembles or to do chain multiscale to solve the inverse problem of calibrating potential on this reference here. It's an initial distribution of vacancy formation energies associated with the training database that I used surrogate, and then I can condition that on surrogate data and come up with a posterior distribution of potential parameters that you need to represent that observation. Ian talked a bit more about this on this poster as well. But I guess what's more critical than that, as we move to high-dimensional interatomic potentials that don't have a small fixed number of parameters, is starting to quantify model form area. So where we don't just vary parameters for the Jones type model, but we draw samples from some distribution of functions, and perhaps specified by a mean and some non-parametric deviations from. So this is, yes?
So you say so your compound model by changing the functional form, but where are you drawing this? What's the distribution?
I'll get on to the more specific example in a minute. But, you could view this as a Gaussian process with a given mean function, and then we need to specify where it's going.
Oh, I see it.
So that's probably a good picture to have. So this is the way that the predictive variance has been used in GP-based interatomic potentials quite successfully, but it's hard to get quantitative predictive accuracy for the errors. So this is something that I did with Gabor, Albert, and a few years ago in interatomic potential silicon. We get useful kind of qualitative error indicators from these atom predictive variances. This is the vacancy fusing. You can see the vacancy is well represented to equilibrium points, those that contain the training set, whereas at subtle points, it's far away from anything that is included in the training. Therefore, we get a large errors. But that isn't a quantitative error in quantity of interest. It's an individual uncertainty. So a simple-minded way to go from those lower atom energies through to errors in quantity of energies. It's just to assume that the errors are independent and you can add them up essentially and see how far we get at that. So if we wanted to look at simple quantity of interest, we could consider surface energy, in this case in iron. It's a bit more complicated because our model has two components, treated in the same way essentially. So our surface energy is just given by the energy difference between two sums of things that we predict local energies. They have more up the bulk of the surface. And we can use our surface energy in this way. We can use our posterior variance expression for the individual local energies. And if we just assume everything's independent, we add up all the variances and then we propagate through and get a variance on the total quantity. And in this case, it works out at just over 1% error. If we actually see what the error is with respect to the reference data for this particular quantity, we're overestimating that error that's significant. So the first thing to check is how much of that is due to this assumption of independence. We can address that by, instead of assuming that we can just add up all these variances, actually sampling from the posterior EB, so just sampling from the multivariate normal given by the posterior mean and the posterior covariance, and that gives us this distribution of samples shown here in blue. It's the correlation between the error. Yes?
This presumably includes all the atoms in the.
Yes.
So if I make the unit cell infinitely deep, it will not affect your prediction after 5 layers.
Yeah.
Your estimate for the average, for the error will diverge. Is that correct? Do I see what was doing correctly?
Which line will diverge?
No, I'm saying that because I'm making a 1 milli error per atom in the bar. So
Yeah.
if I give you infinite bar, even this improved error estimate will come back with unbounded errors.
I don't see where that is, but maybe we'll have to discuss it more.
Okay, good.
So yeah, the error is getting a bit smaller once we take effect of the correlation between the individual.
So if you did that,
Yeah.
perhaps a way of, so if, let me see if I understand correctly. So let's say that you have two unit cells of ideal bulk.
Yeah.
The first way would tell you that there is an error in the difference in energy between these two,
Yeah.
right? Whereas the second would tell you that the error is zero. Is this correct? Imagine that you are computing two, primitive cell and a conventional unit cell. You compute the energies. Clearly, the energy difference has zero error. Must have zero error. But if you use the first assumption, you would get that there is, if you materially compute the difference between the two, you would get a zero error. Is that correct?
I'm adding these errors. Right.
So in this, yes, exactly. So the error would be non-zero,
Yeah.
right?
Yes.
Whereas with the second case, you get zero error. So with the second, by sampling the posterior, you get zero error.
In the infinite case. Why would you get zero error?
Because you are computing the same identical thing, you just computed it twice. And just the errors clearly are definitely not independent.
Yeah.
So in the second case, you get correctly that the error is zero.
Exactly.
Okay.
Does that resolve your question? Yeah.
I don't see where you take the surface energy is the error between the surface total energy.
Right, but the variances have to be added.
Right. So but you're taking the covariance of the atoms in the surface unit cell and the bulk unit cell
Yes.
also.
Yes.
Okay, that's my question. And it does resolve. Yeah. Very good.
Right, so again, we're still overestimating compared to the true error. Maybe that's the question. Maybe we shouldn't expect to exactly hit the errors. Correlation effects and use. In order to simplify things, I've made a pretty much specifically for this workshop, I hope it's going to be useful to discuss a simple example together with Albert of a bunch of diamonds and triangles. I put more details in this paper that I set up on the upload yesterday, so it's not good equation afterwards. And essentially what we do is we have a 2-body plus 3-body model. We're training it just on a very small amount of data, and holding back almost all of it for testing, so that we can try and say something about how useful the error was. The changes that I made over the standard GP framework that I'm including on explicit basis set contributions to zero position. So the forms of this all is basically equal. So we have GP flexible contribution zeroing in, and then we also have an explicit basis set. This is similar to delta learning, we have just some difference between the baseline model, except that this beta here is a random variable rather than a fixed deterministic quantity, and it will also contribute to the fixed uncertainties. For the free body function, I'm just using standard GP. And then what I do is take a prior for the weights on the fixed basis functions, which has some mean and variance matrix, and then you can marginalize the weight, integrate the weights, and you get a new GP. Pointer, where we get some mean that depends on the weights, and also a contribution to the uncertainty rising from the variance on the basis function. That's what's shown in this picture up here. This is the explicit basis. It's a relatively small contribution to uncertainty from that in this case, whereas most of the uncertainty is stemming from long distances from the non-parametric. So blue have two contributions. Okay, that's a bit unwieldy to work with. We can make things a bit easier if we take the limit where this prime becomes very vague. So where the precision is to zero, and then we obtain updated expressions for the predicted mean variance that don't depend on making any assumptions about the mean value coefficients. If we do that, we get standard GP mean variance and the substitution from the basis as well, and then there is this formula essentially for the average weight comes out of building a design matrix, so evaluating the basis functions and whatever. This is basically the same as doing the operation. Okay, and what I'm going to do for my basis set, my Argon things is use the Jones type basis set, and I'm using standard squared exponential vectors. It's going through with the start, and then I'm also putting in Gaussian likelihood. So I'm assuming that the observations of the energy that come from quantum chemistry method match this model on average with some massive noise. That gives us 7 hyperparameters that we have to optimize. What I want to kind of explore a bit is how important it is to do that, and how to do that, picking up a bit on what I showed yesterday. So if we use the standard heuristics that we've been using in GAP typically, which is where the equations up again, where we use physically informed intuition for these length scales, and we take the energy scales in order to balance the energy contributions from the two terms. Then we get pretty good predicted accuracy on the mean, but we're a bit pessimistic about the uncertainties. So we get quite a large predicted error, and the true error is pretty small. If we optimize the log marginal likelihood, we improve the fit, so the reduce their error goes down a little bit, but we don't have very good correlation between the true and the predicted errors. They're all a bit smaller, but we don't have good correlation. This is the usual GP log marginal likelihood, except for these two extra terms here, but they're the explicit basis set. Those are included in the optimization. I'm not sure if that's a super important ingredient, which I'll also go back and try checking them out. But what I tried next, and I think this is maybe the main sort of last point or takeaway point, is really sort of renounce this this fully Bayesian approach where we think that the log marginal likelihood is the key quantity that describes the probability of the data given the model, assuming that the model assumptions are correct. And we instead look at a more sort of frequentist approach, which is this lead one out cross-validation style approach. Then what we get is slightly worse fit overall, but pretty good correlation between predicted and true errors. I should unpick this a bit more using the improved analysis approaches that we heard about from Pascal yesterday. But the intuition behind what's going on here, this lead one out cross-validation likelihood consists of fitting the data on all possible subsets, or we leave out a single piece of data. So that means connections we made with what Michaela showed yesterday. And crucially, it doesn't rely on the assumptions of the model being correct. So we don't actually use the model anywhere in this optimization. So that's the main thing I wanted to say. I'm running out a little bit of time, but just got a few things that we might want to talk about in discussion sessions. I think there's a lot we can do with statistical UQ methods, but we have to keep in mind that we're effectively conflating things that are not really statistical errors with truly statistical ones. That's something that we're talking about in the discussion. Gaussian likelihood models are very appealing because we get analytic solutions, but we should consider whether true distribution of differences between our models and our data really is Gaussian. There are different ways to do that, but the explicit basis functions I mentioned is one way to put a bit more physics into model. The non-parametric that's work to do. We could formalize that a bit more with hierarchy of models. Following sort of Kennedy-O'Hagan approach, where you have one model which is calibrated on the outputs of your reference computational code, and then you add to it another model which has a parameter that forces it to be smoother, but depends only on physical inputs, not something from there in this space. And maybe the likelihood isn't the best one. We should be looking at we need to do faster tails or other ways of distributions. And then this last point that I made about optimizing the marginal likelihood might not always be the right answer, depending on whether the model scalable at the Okay. Ideally, of course, we could do this properly, fully Bayesian way. We sample overall hyperparameters. That's at least for large training sets. There might be ways to do that approximately with variation inference or likelihood free inference. Explore some of those approaches. Let's finish by thanking everybody who's contributed and from the agencies. Hopefully, some very good questions. Let's take somebody back up. I must have one more point to. Yes, please.
Just a quick question. Go back to one slide.
Yeah.
Sorry, that's all.
Yeah.
So, are those hash points the averages over bins, or
No, this is all the data. The training data is on orange. So that's a random subset of all the data.
So what is going on when you have? So are you saying that the distribution of errors is strongly peaked, very much at like a finite number? So your distribution of error is very far from being Gaussian. Points are not scattered around zero error; they're scattered in a very concentrated way around.
In this panel or in this panel as well?
On the far right.
Yeah. So there's something systematically missing from the model. Is that your suggestion?
One, I'll just ask the other.
Yeah. This is very recent and I haven't dug into it in that much detail yet.
Can I maybe comment? In our test, just empirically, we've found that optimizing hyperparameters in some cases gives you error that tracks the predictive uncertainty. So I don't know, maybe it depends on details, but also theoretically, I believe there was a proof, I forget where I saw, that likelihood optimization should be equivalent to cross-validation if you sum overall sort of p rebound things. I forget exactly, but so there should be correspondence and close connection. Why would it be different?
So I think it's precisely because of the marginal likelihood only applying if the assumptions of your model are correct. So if you do have Gaussian,
Also, you think it's related to the Gaussian distribution?
or other assumptions on parameters.
Okay, in that case, it's a testable assumption. So
Yeah.
okay, that answers the point.
But I also wanted to mention that this is no more expensive than optimizing the marginal likelihood. So what we have to do here is effectively invert the covariance matrix once, and then delete rows and columns, and get the inverse for the reduced matrix. The formula to do that, which are relatively cheap. So it's not that this is a super expensive thing to do. It's comparable.
Yes, double.
Can I go back to this plots?
Yeah.
So I have a couple of questions. So yesterday we've seen this distinction. So the distinction between errors and uncertainties, right?
Yeah.
You're not supposed to be able to predict the error.
Right.
So, and the left-hand side, that's sort of what happens. You have no points on the bottom right triangle, but you can have low true error and high predicted uncertainty, and that's in fact what should happen. So Why has that disappeared from the middle bottom?
So I think the middle bottom is somehow getting stuck in a bad choice of hyperparameters. I repeated the.
But it's the same with the loop, right? You don't have any points. You have high predicted error and low actual error. So that's weird. That shouldn't happen.
So I agree that you shouldn't have perfect correlation, but I would be happy to have a bound around the identity.
Yeah, but if you have a band, I can get a better one.
Well, no, not necessarily, because it could be either side, right? It could be that you're really good at predicting, but it can't be, it's like,
Yeah,
like,
I can make a better one. I can make two better models than one.
yeah.
Well, that's a very weird error.
Yeah.
I think the main point I want to make is that hyperparameters matter. We can take that away.
But they both could be stuck in weird. My problem is they both could be stuck in
So I repeated the optimizations 100 times from different starting points. I tried to correct for that, but
if you zoom in, because the errors are, the maximum error is 3 times bigger on the loop. So if you zoom in, what happens? It's just
it kind of fills the square, basically. Yeah. So it's really a lot worse than the starting point. There's something to learn from that. Yes.
So was this fitted with the same, but this is all gap or what's the?
It's not in gap code because I wanted to be able to optimize everything, but it's in the spirit of gap. Yeah.
Sure. So did you try different model shapes essentially? So different hyperparameters like polynomial degree and other things? Because
Like what, sorry?
like polynomial degree or some convergence parameters. So what I've seen is that if you have essentially the wrong model and you optimize hyperparameters, this correlations you get bad correlation.
So this is a very simple model. It's only 2 and 3 body.
Yeah. Okay. So what I would perhaps think could be happening is that essentially if you would add basis functions essentially, in turn increase the marginal likelihood just because they capture more of the actual potential energy surface, and that also in turn greatly improves the correlation. At least that's what I've seen.
Okay. Yes.
Yeah, maybe if I could ask maybe more philosophical question. So on the previous slide, it was the function of R. I think the GP has the uncertainty explode as R goes to infinity, right? Following forward.
Right. So that's beyond the cutoff of the descriptor. What's
Right.
going on there?
So I guess my question is like, to what extent do I expect these GP uncertainties to be realistic in some sense, right? Is there some way you can inform what you would expect my uncertainties to be as a function of R?
So in this case, that's just coming from this prefactor, right? There's no data, very low data there. So you shouldn't really read anything into behavior beyond 7. I should probably have cut the plot off a bit closer.
But, even I would have maybe expected more uncertainty for closer distances too.
So I think that's maybe taken care of by the very good match to the hardcore repulsion in this case, because when you put 2 ion atoms very close, it really is quite close to 1 over r to the 12. By including that divergence in the explicit basis, we don't have that much uncertainty. That's my attempt to explain that, but I agree that there's more.
Could you go back to the very beginning when you talk about exchange energy development? This is quite interesting. Something I started worrying about recently. Did I mention that you're using experimental data, right? That's the trouble with any data-driven model. But one could imagine using some higher theoretical data to develop better functionals this way. Yeah, that's absolutely. Yeah, it's quite interesting. Okay, that's great. I should take a look. All right, if no other questions, let's thank the speaker. I believe we are perfectly on time for the coffee break.
There's the opportunity for that.
Exactly.
Free. Okay.
So what I want to talk to you about today is joint work from most of the MIT seismics group, so myself, Joanna, Giant, Yusuf. And I want to try and string together enough obvious and non-obvious statements in a row to hopefully drive some sort of discussion afterwards. That's my ultimate goal here. And I decided that I wanted to do something interesting and try and raise as many questions as I can and answer as few as I possibly can. And ultimately, hopefully to show as few results as I can in the hope that I can drive discussion for the rest of the week. I was also tempted to label this talk, How I Learned to Stop Learning and Love Uncertainties, because I think what I really want to try and convince at least some of you today is that appropriate estimation of uncertainties really is critical to driving this entire activity process. So first, I'm going to show you why perhaps if you are not careful about probabilistic modeling of your data, then your inference is likely to fail, right? And then hopefully I can also convince you that even if you're probabilistic taking your data, if you aren't careful about the Bayesian probabilities that you get, then the rest of the cycle also somewhat fails. So there are certainly nuances in each part of this approach. And what I really want to do is focus on a very simple problem, because as a mathematician by background, I like to work on small problems. And so the particular thing that I'm interested in is this cluster, this very small cluster of 13 Lennard-Jones atoms. And they have a very interesting behavior where they have this unique geometry that occasionally rearranges itself in some sort of rare event fashion. And so the ultimate question I'm trying to do is I'm going to try and fit a radial basis, an ACE using an ACE framework model to data, and then hopefully understand how sensitive is my estimate of the rearrangement time to whatever errors I might induce fitting my potential. So this gives you somewhat of a graphic of what I'm trying to estimate. So of course you might be able to work out the exact rearrangement times analytically, but this is just a histogram over some 1,000 or 2,000 samples of running at deep for long trajectories and estimating this rearrangement time. And I kind of give you a graphic showing what these different rearrangements look like. So of course, this is the distance from the centroid, and one atom starts in the center, and then every so often this rearranges itself. In this particular MD trajectory, this rearrangement happens very quickly, but of course there are other MD trajectories where this takes a rather long time. And so when I talk about fitting, this is essentially the data set that I'm going to have to work with. I have some very long MD trajectory that forms my data set, and there are certainly complications I'll get to involved when we do that. So first I want to say, what would be the naive, most basic thing that you would want to try to do? And as you would say, well, maybe I just select some large subset of my data, take maybe my entire MD trajectory, set out 100, 200 configurations randomly, maybe every 100 time steps, 1,000 time steps, something like that. You select some appropriate radial basis sets. I use a particular linear framework to do this, and then you fit data using some maximum likelihood approach or maybe something else. And I mean, if you just look at and plot the energies and forces as a function of distance, it looks like you fit them spot on, which is what you would expect, right? Because this is such a simple potential. And I even plot the errors as a function of distance here. And so there's some structure here, but the errors on the order of 10 to the negative fifth. These are absolutely minuscule errors that we're dealing with here, much less than you would see in maybe larger simulations. But of course, the moment you try and run long-range molecular dynamics with this, you understand that actually I'm not doing a very good job of fitting my potential energy surface at all. In fact, I have quite significant bias if I look at the energy over my MD trajectory, and that results in a dramatically underestimation of my rearrangement time. So this is quite puzzling, of course, because how do I square these two facts that it appears like I get my energy and forces quite spectacularly, but when I run long MD trajectories, this particular QOI, which might be more sensitive to differences in errors, is so badly estimated. So hopefully that has piqued your interest at the beginning. So now let me take a small detour. Oh yeah, sure.
So when you use ACE, but you do pair potential ACE or you know?
Yeah, just the radial base.
So it's just a pair potential.
Yeah, essentially, right, yeah. And in this particular case, I mean, since it's just a cluster of 13 atoms, right, we don't have to worry about cutoff radius effects into that. So we were simplifying the problem to try and.
I just think it's really good to try to see what happens. So if you also include higher of all the other terms, if they, because you can fit different ways.
So what happens is they decay quite rapidly, right? The corresponding fits after, if you include 3 or 4 body terms, you know, the corresponding contributions are 10 to the negative 12 in terms of the parameter size. So they decay quite rapidly in this case. Yeah. Which I guess I would hope would be the case. Yeah. Right, so I want to talk a little bit about Bayesian methodology and the hope of not using too many equations, but to describe just very briefly what I'm interested in. And ultimately, when we're talking about Bayes' theorem, we're really only talking about 4 components of it, right? And this combination of likelihood, prior information, model evidence, all are contributing factors into your posterior distribution. And in particular, I want to try and call attention to maybe nuances when you go and make choices in each of these particular elements. For example, the construction of your likelihood, you make it Gaussian or not Gaussian, that depends on what model you're using. But even the prior information, which is essentially supposed to be a understanding of what expert knowledge you have about your potential energy surface, about the parameters itself, and how can you codify that in some probabilistical language and use that as a quote unquote prior information, not necessarily just using standard normal Gaussian. And then something that I think is also unappreciated is the contribution of model evidence, particularly how do you select your data, which will be an important factor. So I want to go just somewhat quickly through a list of different options that I've seen, because I think we've all seen them over the last 2 days or so. The most likely thing that you would want to try is just keep everything Gaussian if possible, because of course, if you have normal distributions, you can get committee members very easily, and then you can do active learning using that. And so typically what you see is maybe you choose some Gaussian likelihood, and then you choose some weights for the energies of the forces that should actually represent your actual uncertainty about the data that you're using to fit, in some sense, the covariance matrix. Maybe you choose a sampling distribution. So this would be more like a statistical approach, like a cross-validation, where you choose different sets of your training data and you fit each different training data set and use that as a sampling distribution. That's another formulation. Maybe you can do what has been suggested before, you do simulation-based inference. So you dispose with this linear relationship and you say, actually, maybe I'm interested in fitting to certain properties of my potential energy surface instead. And then, of course, there are several different attempts at priors, but really what I want to point out is that typically what happens in these Gaussian cases is that the more and more data that you include in your fits, the IID assumption that you make when you're imposing a Gaussian distribution on your fit means that you can get vanishing variance, even though your model may be misspecified in some sense. So I think we had a nice demonstration at the beginning of the last presentation that clearly there was a mismatch between the function he was trying to fit and the radial and the basis set that he was trying to fit with. And regardless of increasing as much data as you can, you get smaller and smaller estimates of your error, even though your fit's better. And so this assumption of Gaussian error should definitely be viewed with suspicion, and particularly if you expect that model specification occurs. But more importantly is this, I feel like we sweep under the rug all these choices of hyperparameters that are typically included, right? So we mentioned this a little bit earlier today, but what weights do you use? Do you consider those hyperparameters? What do you do with the radial cutoff function? How many basis members do you include in your basis sets? There's all sorts of hyperparameters, and do you actually try to incorporate uncertainties from those hyperparameters into your posterior predictive? But really what I would like to take away is that none of these, all of these strategies that I've listed today, none of them really focus on components of the potential energy surface that you're estimating that are informed by data. And maybe what I really want to pitch to people is that it's important that we don't just fit priors that are normal distributed with mean zero and scalar variance. Because in particular, what I've seen over the last few days is that people have all sorts of heuristics that they use in order to correct what they're seeing as model error, right? They choose weight matrices as part of their covariance matrix, or they have certain cutoffs. There's a lot of heuristics, right? But what I'm trying to pitch to you is that if we together can incorporate all of those into a probabilistic language, if we can form a meaningful prior, then we have additional power because we can then ascertain to what extent our data is truly informative of our potential energy surface. So we can analyze which directions are data informing our model, or which directions are more informed by these prior assumptions that we're making, that we seem to have all this expert knowledge. So there were a couple more attempts, back to the story, the Leonard Jones story. There were a couple of different attempts to try and rectify the issue before. So one attempt is, okay, so maybe I shouldn't just take one training data set and fit to that one training data set. Maybe I should take multiple training data sets and form a committee based off of fitting all of those different data sets. And so I do this, you can optimize all the parameters for each of those different training data sets, and the effect is actually worse than before. We get a much narrower estimation of the rearrangements. And so attempt number 3 is like, okay, maybe if I include a large enough data set, but then if I try and be intelligent about using Bayesian fitting, so maybe I go out the walls to include some particular form of prior, I'm careful about fitting my variances, and then when I sample and I run my MD trajectories, I sample coefficients from my Bayesian posterior along with random seeds. So I do this kind of tensor product independent sampling. And the good news is that I get a greater spread in my estimate of variance. So something seems to be meaningful when I do this type of work. But in the end, we're ultimately underestimating some of these long tails that occur in the variance. So maybe what we became to realize is that no matter how sophisticated you are in the fitting process, if you feed bad data or maybe uninformative data into your model, you can only do as good as the data that you give it. So you should really be very precise about what data that you're choosing to feed into your model. And so this is where—
Can I ask you a question?
Yeah.
So do you get any indication of the fact that the model would fail so catastrophically from the error, the cross-validation error and
I'll talk a little bit about this in a few slides. Yeah, so, but there's, in a normal problem where the errors are much larger, it might go undetected, for example, right? So it's kind of curious a little bit. But this is where I want to turn the Bayesian methodology into now a discussion about active learning. And the sense is, well, maybe we really need to be more careful about what data we select to go into our training data set. Is it not enough to consider just randomly sampling my MD trajectory and then hoping that the distribution of errors in my training data set is useful for fitting my model? That's the ultimate question. And so what I want to propose is really a generic, what I would call a kernelized active learning approach. And so what I'm going to propose is using kernels for each component of this active learning process. So initially, I'm going to talk about what are referred to as determinantal point processes. I'll describe those. We use those for subselecting training data. Of course, as we've seen throughout, there's been discussion about using Gaussian processes. Those are, in a sense, also kernel functions. But then later, I will talk about this technique using kernelized methods to perform modified molecular dynamics for generating configurations. Okay, so I want to talk about DPPs, or so-called determinantal point processes, which actually have kind of an interesting history to them. They were first identified in 1975 as being fermion processes. There's some work that led to this theory that is associated with the so-called anti-bunching effect. But really, I'm going to describe to you a more mathematical framework. And so I'll say a point process is simply a probability measure on, say, a data set of choosing a subset of that data set. So it's a particular type of probability process. In particular, a determinantal point process is such that the probability of drawing some random subset of my data is exactly proportional to the determinant of the submatrix corresponding to that subset. So I'll repeat that again, right? So imagine I have some very large similarity matrix, right? So I'm trying to compare atomic configurations against each other. And that corresponds to maybe I have 5,000 training configurations. So it's a 5,000 by 5,000 matrix. The probability of choosing some rows and columns of that data set is exactly proportional to the determinant of that submatrix. And so why is that interesting? Why is that a useful thing to consider, and why am I proposing it here today? Well, it has a very interesting interpretation in the fact that in the linear case, this is exactly devolves into what's known as de-optimality, right? But in the nonlinear case, it's generalizable to other approaches. And so essentially what we're trying to do is maximize the volume of descriptors in some sense. So the prescription goes as follows. The DPP kernel is a very flexible approach where you need to specify first a function that encodes diversity between two different configurations. So this is a critical component. I need to know how to differentiate between two different atomic environments. I need that to be useful in some sense. And the second component is a quality term. So you as a modeler, when you're trying to form your data sets, you might have various different classifications of data. And maybe you as a modeler say, I want to include atoms of a higher energy or configurations of higher entropy. There's some sort of quality term that you want to associate with some configurations to make them sampled more often than others, for example. And so you can encode all of this information into this DPP model. And then what happens is when you sample the DPP, it gives you a sample of your training set that is diverse in the way that you specified it. Okay? It's diverse in the sense that we're trying to maximize these volumes of descriptors. So what does that look like in this particular problem, right? So you have to specify some sort of kernel, right? So since we're using kind of an ACE formulation, we have ACE descriptors, and then we can perform great distances based off those ACE descriptors. And then we can plot. What I've done over here is overlaid the so-called inclusion probability, which is how likely am I to include a particular training configuration into my training data set. And what I'm plotting in black is if I ask my DPP what would be the most likely set of 20 configurations, I can get the mode, right? The most likely set of configurations to be. And so these are actually interesting because they align with what you might intuitively think should be associated when selecting training data sets for this. So notice that the peaks in the inclusion probability are somewhat mostly correlated with turbulence in the rearrangements of this atomic process that's ongoing, right? So clearly you can see the peaks with this turbulence that occurs here, but also the different rearrangement times that occur. And then during times of somewhat stability, you see somewhat lower stabilities. So this is a good check that this metric that we're forming does what we might expect it to do. The non-intuitive thing is that if you ask the DPP mode, or what the mode is, it doesn't take only configurations from the high energy portions, right? Because the bad thing that would happen is if you only picked configurations where something interesting in your dynamics happened, well, all of a sudden, those configurations are actually very correlated with each other. They're too similar, right? So the DPP mode spreads out your configurations in a way that it maximizes, again, this view of volume in this descriptor space, right? And so it does, we can model this probabilistically. The interesting thing too is that this is a stochastic process. So if you want to form a committee of machine learning models or ACE models or something like that, you can sample efficiently from these DPPs in order to get diverse data sets so that each of your committee members sees diverse amounts of training data. So what is the effect of using this? Well, if you look at just the RDFs, essentially, as a function of distance for the data contained in these different ways of sampling your data set, you don't see much variation between these DPP and the random configurations. But where you do see a difference is that in the histogram of energies associated with the configurations, clearly the DPP is biased towards slightly higher energies. And we saw that kind of before that. We're expecting to get some configurations that are associated more with higher energies rather than low energies. But this is not necessarily guaranteed if you're taking some subset of your training data.
What are you using as the distance metric between a speech basis and does it matter?
So on this problem, it matters a little bit. We've tried maybe 20 different combination of the descriptors, because you can use global descriptors, local descriptors, force, or some other summary of that. In particular here, I've had some success with using local descriptors and then a distance, like a Riemannian metric on the local descriptors, which are matrices. But I have to say that using just any of those DPP methods improves the fits quite dramatically in this case. But I will say that that's probably QI dependent, right? So you have to test it for individual models. So what I'm showing here, these 4 columns are associated with kind of these 4 different techniques that I described. So first, if you just fit maximum likelihood estimates based off of random sampling, that's the first column. Maybe if you choose one particular data set and then you use Bayesian fitting and then you get some posterior distribution, that's the second column. Maybe you do maximum likelihood estimation, but you use DPP sampling. And then the last column is if you use the Bayesian posterior associated with the DPP log. So these cover a variety of techniques, but what I will say is that the most important thing I want you to take away from this slide is that what happens is if you divide by the standard deviations of predictions of all of these, you see immediately that there are significant biases in fit as a function of the variance of your estimates, right? So you're asking, what indications did we have to say, like, maybe this would fail so dramatically? And the indications appear here is that the errors on the previous slide are quite low, very low errors. But if you divide by the variance of your estimates, the standard errors are quite large, quite significant, right? Where I would expect my errors to be somewhat normally distributed if I have an effective variance, right? Of course, if you just look at the errors on your test data set as a function of configurations, you don't see this structure. It's only in the case of this 2-body pair potential where we are allowed to view things as a function of distance that this structure becomes a little bit more apparent. And quite surprisingly is that there's significant structure in the errors of your forces, whereas in the DPP mode, the intelligent sampling is able to get rid of some of the structure in your forces, which would lead to better calibrated results. So what's the almost end of the story is that if you do all these things, you still have a slight bias in your energies, but we're much better able to fit the rearrangement times. Yeah, so that was an interesting story, maybe at least for me, but it's not necessarily the end of the story for me today here, because I want to continue talking about this kernelized active learning method. So I'll make it somewhat brief, but as I mentioned before, each component of this active learning framework you could view using some sort of kernelized method, just like the DPP samples use the kernelized method. What I want to share with you today is an idea for using kernelized modified molecular dynamics in order to ensure diversity in your data set when you need to generate new data. And so what does that look like? So what I'm disguising here is essentially molecular dynamics. I written it in a very particular way, but you imagine I have some configuration driven by the gradient of my energies, so some sort of forces are combined in there. The unique thing here is that the way that this is modified is that I imagine I have a set of initial configurations. The force that one configuration feels on all of its atoms is actually smooth over all of your configurations. So it sees a smooth version of the atomic forces. In addition, there's a repulsive term here, a gradient of your kernelized method, matrix. And what does that do? It makes sure that no two sets of configurations are too similar from each other. And so why is this an interesting thing to do? Well, it so happens that from other aspects that we're working on as a group, that you can take advantage of so-called interacting particle systems, of which this is a particular type. And because these L's are kernels in some sense, you can take advantage of theories that we know from our KHS systems. And essentially what you can be guaranteed is that if you perform molecular dynamics in this way, it reproduces so-called quadrature points at your potential energy surface.
right? So you can be guaranteed in some sense that I'm still leaving my underlying distribution invariant with this particular form, but I'm also able to achieve some notion of spreading my configuration out in some sense. The other benefit is, like opposed to some active learning techniques, this process will converge at some point, right? You don't have to keep running it every so often. Say, okay, I'm going to stop, see if my error is too large, and then take that configuration set. So I want to play you a couple of videos really quickly. I'll try and wrap things up. So on the left, this is just running regular molecular dynamics for this Leonard-Jones potential, and it bounces around. Of course, I've subsampled quite rapidly in order to make it an interesting video. So the question is, what does this kernelized modified molecular dynamics do? Well, it's certainly more smooth, right? But also you can tell that it allows a greater degree of freedom between these configurations that you wouldn't otherwise see. So what is the effect? Well, if you look at, here I did a naive thing, and I'll talk about this later, is that if you actually were to run, say, 20 sets of molecular dynamics simultaneously, do that, which is probably the naive thing to do, you would do that in practice. But you can see the potential energies start to diverge in a set, right? So it's ensuring that all of these different configurations that you're running have different potential energies associated with them. The other thing that I'm plotting here is the log determinant of my kernel matrix, which again is a representation of how diverse are these different configurations. So when I started, I just randomly sampled 20 configurations. They were not very diverse. The log determinant was quite small, meaning that there was significant overlapping information between my configurations. And quite rapidly, the log determinant increases, representing that this kernelized method does, in some sense, produce diverse configurations over time. So what you would probably do in practice is actually you run molecular dynamics, and then as you pick up configurations along the way, you would add these into your kernel method. So you're not necessarily running 20 different empty trajectories at the same time. And I don't necessarily want to make too much of a point, but the end result is that it improves fitting, even if you use a small number of configurations. Okay. So what do I want to conclude with? I want to say that the variability of your data set is extremely important, but also is a representation of the errors that you have. In particular, this notion of, in order to have adequate probability estimates of uncertainty, you also need to be careful about the choices of your data set, and active learning depends on each of these very crucially. There are a lot of areas of continued work here. In particular, I want to highlight a couple of things I've been thinking about that go more to the fitting, is that can we use particular QOIs, or maybe just more generally particular prior knowledge that experts have in order to inform the prior densities or to do dimension reduction in some sense. And then also continue discussion of, since these kernel methods rely on some aspect of comparing atomic environments, it's very important that we understand what the geometry of these spaces look like and how best to represent some different atomic environments. Hopefully I didn't go too much over, but appreciate your time. Questions?
I certainly have, but James.
You talked about the importance of encoding all your information explicitly in the file. What did you use here for Leonard-Jones?
We're currently in the process of using a variety of priors. We use the basic thing, normal, mean zero, but also learned mean and learned covariance, and also informing some sort of sorry, what am I trying to say? Smoothness in the prior, right? So if we can minimize wiggles, so you can encode that in a linear operator potentials. In this particular problem, there was mixed results on using on some of those, but they were better than not using any sort of regularization. So there's a variety of techniques. All of them not necessarily satisfying at this point in time.
Okay. Ask a question on the, so I found these results really puzzling, you know, like what the kind of puzzling. So I didn't understand some of the figures that you were showing. Did you show at any point the pair potential predicted from your model? Yeah, because I didn't understand if these wiggles were actually the term.
Sorry, yeah. So you can see in this top left-hand corner, I plot both the actual Lennard-Jones potential and the prediction. They're just overlaid, so you can't visually see a difference between the two, and that's because the errors on the order of 10 to the -5.
And you're saying that these minuscule errors can
In this particular QOI, which we all have Michael to blame for because he suggested it, which maybe is an outlier in terms of quantities of interest that we're interested in, but for that particular QOI, it's extremely sensitive.
But what happens? Okay, so sorry, but I don't believe that the potential that looks at this and that is where you never observe during your run. I don't know that some particle will go outside this range in either direction. I don't believe that it will be. I'm sorry, but I just find it. We all, this is numerical noise level.
Yes.
There are splined Lennard-Jones potentials that have a larger error.
Yeah. Well, I think the issue comes down to this small but important bias as our approach is, between the range of 2 and 3. There is a small but non-negligible bias that my current working theory, because I agree, I am quite puzzled by these results. But for these interactions of this range, having that bias affects it.
What temperature are the distributions
And reduced coordinates or units, I think it's like 0.65. It's not quite liquid, I forget the exact number.
But I mean, because here you're using EV, so I was kind of thinking in terms of actual temperature. Here you're using a physical energy.
Oh, yeah.
Because I mean, almost liquid.
So it's still solid, yeah. So that's the only way you can get these rearrangements to occur. Because if it's liquid, then the particles just flow around. Yeah.
But I find this would be really interesting to look a little deeper.
And the puzzling thing is that I can make larger errors. That's what I do here. The errors on some of these are 2 to 3 magnitudes larger at times, but the particular QOI, I estimate better.
So what if you follow? Sorry, if anybody wants to interact.
No, I'm not really that. I was about to ask, like, on the last, do your errors go down even more? But if they get towards magnitude larger, and now, so are there any other parameters which this QI is incredibly sensitive to in the same way? So are there other things that you've changed a tiny bit and also seen a huge variation?
So we're trying right now to understand what part of our parameters in the potential energy surface is this QI so sensitive to? Still, we're trying to figure that. We don't know exactly, right? But I imagine it would be revealing in some sense because it's not obvious right now. That would be.
But if you do and nudge the last, because one thing that makes these things more complicated is the fact that you have a D, you have whatever. So if you do an ED calculation of the process, so that you have a minimum energy path, and you plot the prediction along the minimum energy path, you find differences that are comparable with KBT that justify this massive difference.
I would have to investigate that.
It's really
Could be an interaction with discretization of time.
Yeah, how are you doing? What kind of MD are you? MD bits.
It's a strict modular.
Overdamped Langevin.
Yeah. And I have played with DT, right? To an extent, right? But I haven't noticed a huge impact, but I could investigate further, perhaps.
So expanding on this, so one thing that might be interesting is to look at the barriers, the energy barriers, and see if maybe the energy of the barrier is less.
Well, that's exactly what I think is the problem, right? It thinks the energy barrier is just low enough that it's able to escape more
The fuel potential is very good for Bayesian.
Surely the only barrier is if this is the full show you this two-body, and if you get the energy everywhere exactly, surely it's unlikely that you're going to find like configurations where this gets. The reason I say this is because in your final fit, the errors are genuinely large. So
Yep.
unless there's something that just happens to get something else much more accurate.
I think it's just that there's some combination of, as long as I can over and undersample to some extent, maybe individual coefficients will then overestimate or underestimate my rearrangement time. But as long as I sample these in the sampling process, I can get somewhat adequate fits in my.
But then the rearrangement time for a system this simple should be understandable in terms of Bennett-Schalder, like you have a free energy barrier, and you have a recrossing, you're doing over Downplunge band, so you don't have any recrossing, right? So it's basically, well, we do have recrossing, have a poor correct variable, but then, Boris?
You had a histogram of your energies, I think on one of the first couple of slides. Can you explain how you got it? Yeah, that's one of the bias one, because the peaks are at quite different energy values compared to the alignment of the pair potential that you showed previously, right? So this is the total energy.
So this is during, I think, over two different induced trajectories with different random seeds for each of the Leonard-Jones and running this particular ACE model. That's the combined histogram, the energy strain that trajectory.
So
I think I
configurations,
self-sample
we just evaluated the two different models, right? So
Yes, yeah. So what I should be specific about here is that this energy histogram is not what ACE thinks its energy is at that particular configuration. It's what Leonard-Jones knows it's this energy to be.
that's the blue, right?
So what I mean here is that these two different histograms represent histograms over molecular dynamics chains run by either Leonard-Jones or ACE, but the exact energies that I'm showing are the Leonard-Jones energy of each of these configurations, right? Because it's very possible that ACE mislabels the energy of where it's located, right? But only the Leonard-Jones knows the true energy of where it's located.
I mean, there are two things that can happen, right? There can be for some weird reason, sampling using the ACE potential with downplunge band leads to systematically strong ensemble, which would look like from this, right? Yeah. But how is it possible when the difference in so by looking at the spread here? So the spread here is related to the right? Because these are quasi-harmonic systems, so the spread here is pretty much the temperature. So the temperature here is 20 MeV. Because you have 13, no, and if you look at your Leonard-Jones, your pair curve, the error is 2 orders of magnitude smaller.
I began this talk by hoping that I could raise more questions than I have answers for. I think this is the case, yeah.
On the last slide, you said that it could be because your new process underestimates
Better is a nominal term. I guess.
The last slide, your new thing still has bias, right? And is that bias, is that more than your original bias? Because I'm looking at some of these samples, it looks as though they're not centered around 0.
Yeah, as a function of R, the last case is the only one that, I mean, maybe there's some small bias, but it's enough to sample positive and negative errors as a function of distance.
Do you know whether the means of these actually like have a lower error than the original? So if the committees do the means have an error comparable lower than the original things?
Yeah, well, since these are normal, right, you can write an expression. And I'm pretty sure the mean estimate is the mean of these errors, right? So it's possible that there is some bias. There are some committee members that have smaller error. And similarly here, the mean bias might be one way, but if there's small amounts of bias, maybe there's one committee member or something that has lower error. Does that answer your question?
I'm just looking for like whether there's Because if the mean of these was also a higher error than the original of this, then that kind of rules out the idea that maybe we're getting some beneficial cancellation of errors, which is being hidden by the fact that we have a large stress.
Well, if you were only to run MD with the mean, maybe I'm misunderstanding, but yeah, here what I'm suggesting is that it's important to not run MD with only the mean.
Perhaps something like, because of this, if you look, I mean, did you actually compute the pair potential at because you showed it in a fairly narrow range? Is it possible that there is something in the repulsive wall region that would justify this? Because during a transition, atoms get closer to each other than they do. Is it possible that actually outside of the range that you're plotting, there is a substantial difference between the Lennard-Jones and the potential base?
This is something we investigated, and during the Lennard-Jones trajectory, the atoms don't vary beyond the range that I was showing. Although some ACE fits were so bad that
I mean, I'm really hoping that there is a mistake somewhere, because otherwise we can all go home.
yeah.
Just one thing, just can you clarify one more time exactly how you get from the samples you've got in the exterior to the times that you're presenting?
Okay, so in this case, what I do is I run molecular dynamics, and each molecular dynamics run, I choose one of these coefficients at random and one random seed, right? So I do this 1,000 or 2,000 times, right? So I'm sampling over the configuration. But on some of the previous slides, so for example, here, I only sample over the random seeds, the initial random seeds. And here I do sampling over the training data set, so I fit the community members that way. And here I also do what I described at the end, is that I pick one coefficient, one random seed, and I run it in each trajectory. So is that?
Yes. Yes.
Okay, so this was very thought-provoking. I think we can probably go grab a beer.